Good afternoon. Today I'm going to talk about recent work on wireless sensing based on the RFID, and we call this name is MetaSight because we use Metasurface to modulate the non-loss signals. So we are focusing on the objects which are blocked. So RFID can be applied in many scenarios, especially so we need to localize the objects. So RFID localization is an important topic. It has been researched for many years. Even in MobiSys, you can see lots of papers. So if we have a line-of-sight path, the signals available, so the localization could be easier. But unfortunately, if the objects are blocked, then we have problems. So those schemes based on the loss path will not be effective. So fortunately, we have a few solutions for non-loss path-based object. So for example, we can use RFID tag-based solutions. Those kinds of solutions are based on deploying the tags around the object. So the effectiveness of this kind of scheme will be dependent on the richness of the multipath, non-loss multipath environment. And in some scenarios, we cannot deploy the tags around the object. It's not very convenient. We could use LOA-based schemes. So beforehand, in an environment, we just classify the LOA distributions, and we then measure the LOA values of object. Then we do the matching, and finally decide the location. But this kind of scheme will depend on the regularity of the reflectors. So in this paper, we take a different approach. We use Metasurface to modulate the reflected signals so that we can have, we can eliminate the impact from the non-loss path from the environment. So first of all, we need to establish an end-to-end path from the object to the Metasurface and then to the reader. We call this the MS path. Then we could have established multiple MS paths, and we will estimate the channel coefficient of those kind of paths. And based on the phase information of those kind of channel coefficient, we will determine the 3D directions. And then finally, straightforward is based on the 3D direction, we can determine the 3D location. So for this Metasurface, we need to have a functionality of non-loss signal modulation. The first one is a frequency modulation. We need to design a Metasurface so that the frequency of reflected signals can be changed from the original signal, for example, F to the, our desired frequency, F1. So we can remove the interference from the environment. The next modulation capability is phase modulation. So we want to, the reason for doing that is we want to eliminate the impact of the path from the Metasurface to the object. We also want to align the signal from the reflected, from Metasurface to the reader to improve the signal strength. So to have those kind of two functionalities, we design a Metasurface which consists of multiple elements, and we have a controller to fine-tune the phase and the delay of those kind of elements so that we can achieve frequency and phase modulation. So now the channel model from end to end is like we have OM path from the object to the Metasurface, then from the Metasurface to the reader, that's a MR path. So that's a total path, MS path. So the basic principle to locate the object is we look at the relationship between the direction of the object, theta E or theta H, the 3D dimension in direction. So we can derive the relationship between the path length of the adjacent elements, or not necessarily adjacent, any elements in between. We can establish this kind of relationship. And from the path difference, we can derive the phase difference. So now we have a relationship between the phase difference of the two elements and the actual direction of the object. So we can do this on the rows and on the columns. So this is a basic principle we are going to apply to determine the 3D direction. So now we still have a few challenging issues to solve. The first is how can we resist the impact from the MR path? The problem could be because the phase from the different elements could be different. Then how do we improve this signal strength from end to end? Then how can we estimate the channel coefficient in a fast way? And based on the channel coefficient, finally, how can we determine the 3D direction? So let's look at the solutions one by one. First one is about how can we eliminate the impact of the MR path. This is done by MR path calibration. So this step is only done during the initialization phase. So in this case, we assume the object here is known, okay? The end-to-end path, we can measure the phase. And since the object is known, the Metasurface location is known, so we can determine the phase of phi OM, right? And the end-to-end phase phi hat is also known, so we can easily determine the phase of phi MR. And then we convert this phase, to the delay value of the element, and we take the opposite value of this delay value. And finally, from end to end, we don't have the impact of the phase impact from the MR path. So the next problem is, how can we improve the strength, signal strength from the object to the reader? We want to have longer distance for localization, right? So here we will not, so to solve that problem, we will look at multiple elements. We call this is a reflecting window, which consists of multiple elements. So those kinds of elements will work together. So what we need to do is we want to make sure that the elements, their arrival, the signal arrival at the reader should have the same phase so that the signal can, the strength will be improved. So this is like the multiple step to achieve that kind of beamforming. So this is like a concept of beamforming, right? The remaining problem here for this case is we want to make sure the beam formed pointing to the reader. Otherwise, it's not helpful, right? So what we can do is we will search the delay matrix for each element in this window. So as you can see, we look at the first, the second, that's a time axis, and you can look at the right figure, right? That's a corresponding relationship. So when we do this kind of searching, we will look at the signal strength at the reader. If the reader have, we have reached the maximum signal strength at the reader, then we have obtained that delay matrix. And as you can see in this case, you will see the beam pattern will point to the reader. And finally, we will add this delay matrix together with the MR calibration delay matrix. And the entire matrix will be applied to the reflected window. And we finally achieve the beamforming together with MR calibration. So then for the 3D estimation, we know that we need to have multiple signals, not just one path, right? So we need to establish multiple reflecting windows. So what we do is we need to slide the window across the entire phase. But importantly, we need to set the same delay parameters for each window. We cannot use different delay parameters. And later on, we'll explain to you why we will set the same parameter. So now, by doing this kind of window sliding, the window is considered as an element of the Metasurface. And the entire Metasurface actually become a group of reflecting windows. So from now on, we will look at the reflecting window, not just the element. So then the third challenge, we need to estimate the channel coefficient. Now the channel coefficient is only for the window, not for the element, okay? Because all the elements in the same window has been formed, beam formed to the reader. So we want to expedite the process of this channel estimation. So that's why we have to use both preamble and the actual information that the RFID frame for channel estimation. So what we need to do, we use different segments of the RFID frame, and we use intervals in between the segments to tell which one is for the next window. But of course, we need to have established the relationship between the segment and the window. So we use different size of the segment to represent different windows. So now, how can we detect the channel coefficient? So first of all, we utilize the capability of the Metasurface because it can modulate the frequency, right? But for the reader, it can still receive the signal from the original channel. So we identify the original signal sequence. Here we use PN to represent, okay? So, but in the frequency modulated channel, we have a different sequence. That's the sequence from the reflecting window. So then we look at the correlation of those two sequences, then we will get the channel coefficient. So we don't care about the amplitude of this channel coefficient, okay? We care about the phase. That's why we can use correlation here. So let's look at the 3D estimation based on the channel coefficient. So basic idea here is we use the phase differences between the different reflected windows. For example, we take the first window as a reference, then we get the phase differences. Okay? So now you can see that the phase, the actual phase, the absolute phase of the channel coefficient includes the phase from the beamforming, which is a phi RB here. Okay? So remember that we set the phi RB the same for different windows. So that's why we take the difference, that impact from that beamforming is removed. That's why previously we have to say we set the same parameter for different windows. So now we have obtained the phase differences between different reflecting windows. Then how do we determine the directions? Suppose we have the target direction is theta R, theta E, and theta H R. Okay, that's a target value. And from this value, we can derive the phase difference between different windows. Then we will match this value with the measured value. And this is a simple way. Again, this is a correlation. And we take a normalization, and you will see that when this value approaches 1, then we will find out that's a target value. And that's the result to tell you okay, how we approach the maximum value of P, and we will get the target direction. So based on this direction, and then we can easily determine the 3D location. We can apply many existing solutions. Okay. MetaSight has been prototyped. Especially, you can see that the Metasurface itself, it's a very lightweight design. So the weight is less than 500 grams, and it's quite thin. And that's why we can apply this Metasurface to the wall and to the ceiling. And during our design of the Metasurface element, we have considered the mutual coupling factor. So as you can see, the radiation pattern is quite good in this kind of design. We also have a schematic for the controllers, and that includes the receiver and the reconfiguration circuit. So the receiver has been implemented like a whisper tag. It's a low power circuit, but the reconfiguration circuit, we are still implementing that in as a FPGA module. And we have tested the system in different kind of scenarios, like a hall, corridor, room, or library, to represent different kind of non-loss environments. And we have tested obtained the result of the 3D estimation. And as you can see, in different indoor environments, the average angular error is within like 1.7 degrees. And if we also tested different distance between the Metasurface and the object. As you can see, if we increase the distance, the accuracy will be decreased. That's normal. And if we look at the 4 meters between the object and the Metasurface, the angular error is within 2 degrees. Okay? So let's look at location, 3D location errors. Considering a static object, if the object is stationary, and then we can see that for different indoor environment, the accuracy is within 15 centimeters. So if you look at the mobile objects, of course, we are not considering a highly mobile system. Okay, we're talking about a normal pedestrian mobility. So you can see that the estimated trajectory and the actual trajectory, they are matching each other quite well. And if you look at the overall CDF, the average location error is within 20 centimeters. So as you can see, the mobility impacts the accuracy a little bit by a few centimeters. We compared our scheme with existing scheme, and for example, we did experiment comparison with PingA, and in the library case, we have comparable performance. But in some scenarios, you can see that PingA will have problem. The problem for that is because in that environment, we don't have multiple non-loss path. So that will cause location ambiguity problem for PingA. But the MetaSight doesn't rely on that kind of non-loss path, so we don't have that problem. That's why the performance is much better then ping it. So in summary, in this paper, we have designed MetaSight, which is using the Metasurface to modulate the long-loss signals, so the impact from environment will be removed. So to support the localization, we have developed multiple key mechanisms to achieve accurate localization. And the scheme has been, the system has been prototyped and evaluated in different real environments. And in the future, we are going to extend the work by considering the communication enhancement so that the MetaSight can really have joint communication and the sensing capability, not just for sensing. Okay, so that's the end of my talk, and I will be happy to answer your questions.